All right, let's go.
Number 10. The sun itself. 10% brighter, and that changes everything. The sun you see today is not the sun that will exist in 1 billion years. Right now, the sun fuses approximately 700 million tons of hydrogen into 695 million tons of helium every single second. The mass difference, about 4.3 million tons per second, converts directly into energy via E equals mc squared. This is what powers every photon of light that has ever touched your skin. As hydrogen in the core is consumed and replaced by helium, the core gradually contracts and heats up. The higher temperature slightly accelerates the fusion rate. The sun produces incrementally more energy over time. More energy means more luminosity. Over 1 billion years, the sun's luminosity increases by approximately 10% compared to today. 10% sounds modest. It is not. The difference between Earth's current climate and a full glacial ice age, the kind that buried most of the northern hemisphere under kilometers of ice, is a global temperature shift of roughly 5 to 6 degrees Celsius. A 10% increase in solar output pushes temperatures far beyond that range and does not stop. It does not plateau, it keeps increasing. Every 100 million years, the sun grows a little brighter. 1 billion years from now, that increase will be permanent and irreversible from any process operating on geological timescales. The entire solar system is already slowly reorganizing itself around a brightening star. 1 billion years from now, the reorganization will be impossible to miss from anywhere in the system. Number 9. Earth, a desert planet with boiling skies. In 1 billion years, Earth will not be recognizable. The 10% increase in solar luminosity will push Earth permanently outside the inner edge of the habitable zone. The habitable zone, the range of distances from a star where liquid water can remain stable on a planet's surface, will have moved outward past Earth's current orbit. Earth will be on the wrong side of that boundary. The first consequence is the oceans beginning to evaporate. Not immediately, not all at once, but the process is self-reinforcing. More heat from the sun causes more water vapor to evaporate into the atmosphere. Water vapor is itself a powerful greenhouse gas. More water vapor traps more heat. More trapped heat evaporates more water. A feedback loop with no natural stopping point, what climate scientists call the moist greenhouse state. Once that loop begins, it does not reverse. Water vapor rising into the upper atmosphere is exposed to ultraviolet radiation, which splits water molecules apart. The hydrogen, light enough to escape Earth's gravity, bleeds off into space permanently. The oxygen stays behind. This is not a slow trickle. Over millions of years, the oceans drain away molecule by molecule into space through the upper atmosphere. In 1 billion years, the oceans will be dramatically reduced. Surface temperatures will be approaching 47 degrees Celsius on average. The planet will look from space the way Venus looked in its early warming phase, a world entering the early stages of a runaway greenhouse transformation. Photosynthesis will have ended. Carbon dioxide levels will have dropped below the threshold that C3 plants can use. Most complex multicellular life will be gone. Whatever life persists will be microbial, extremophiles in deep subsurface environments where liquid water might still exist. The surface will be largely uninhabitable. Earth will still be there, in its orbit, but the blue planet familiar from photographs taken by Apollo astronauts will be gone. Number 8. The Moon. No more total solar eclipses, ever. The Moon is currently moving away from Earth at 3.8 centimeters per year. In 1 billion years, it will have moved approximately 38,000 kilometers further away than it is today. The Moon's current average distance is about 384,400 kilometers. In 1 billion years, it will sit at roughly 422,000 kilometers. That number has one specific consequence that most people never think about. Total solar eclipses will no longer be possible. Today, the geometry of a total solar eclipse works because the Moon and the Sun appear almost exactly the same size in the sky. The Moon is 400 times smaller than the Sun, but 400 times closer. This precise ratio, the most extraordinary coincidence in the solar system by apparent visual scale, produces moments when the moon exactly covers the solar disk. The corona becomes visible. The sky goes dark in the middle of the day, an experience that has driven humans to record observations from ancient Babylon onward. 38,000 kilometers further away, and the moon will appear smaller than the sun in the sky. It will only ever produce annular eclipses, a ring of sunlight visible around the lunar disk. The corona will never be naturally visible again from Earth's surface. The last total solar eclipse as seen from Earth will happen somewhere in the geological window approaching 600 to 650 million years from now, and then never again. In 1 billion years, that window will be long closed. Humans, or whatever comes after humans, will have no memory of what a total solar eclipse looked like. They will only know the ring. Number 7. Plate tectonics, the engine that built every mountain, will shut down. Earth's plate tectonics is powered by the heat of the interior, residual heat from the planet's formation, plus the continuous heat generated by radioactive decay of isotopes, primarily uranium-238, thorium-232, and potassium-40, deep in the mantle and crust. These radioactive isotopes have half-lives measured in billions of years, and their combined heat output drives the convection currents that move the plates. Those isotopes are decaying. The heat output is declining, slowly, continuously. Geoscientist Qiming Cheng, president of the International Union of Geological Sciences, calculated in a 2023 study that plate tectonics will shut down in approximately 1.45 billion years, within the window we are discussing. When it shuts down, the consequences are enormous. No new mountain ranges, no new ocean floor, no volcanic activity replenishing the atmosphere with carbon dioxide. The carbon cycle, which on Earth operates through a geological thermostat where excess CO2 is weathered out of rock and deposited as carbonate minerals while volcanoes continuously replenish it, stops working. CO2 levels plummet. By around 800 million years from now, CO2 will fall below the threshold at which photosynthesis is possible. Plants die. The oxygen cycle collapses. The atmosphere loses free oxygen. In 1 billion years, plate tectonics may have already slowed to near stasis. The continents will be locked into whatever configuration they drift into during the final stages of tectonic activity. No new Himalayas, no new Atlantic, no new Iceland, a geologically frozen surface on a planet that will still be warm from the sun above, even as it cools from within. Number 6. The habitable zone moves. Mars enters it. As the sun brightens, the habitable zone does not disappear. It migrates outward. In 1 billion years, the inner edge of the habitable zone will sit beyond Earth's orbit, but the outer edge will have moved outward too. Mars, at 1.52 astronomical units from the Sun, is currently too cold for liquid water to be stable on its surface. The average temperature is minus 60 degrees Celsius. The atmosphere is only 1% of Earth's. Any liquid water freezes or sublimates immediately. A 10% increase in solar luminosity would raise the average surface temperature on Mars by approximately 20 to 30 degrees Celsius. Not enough to melt the ice caps overnight, not enough to produce Earth-like conditions, but potentially enough to drive significant seasonal water activity in subsurface environments, and to make the average surface temperature far less hostile than today. Models suggest that by approximately 1 to 2 billion years from now, Mars will be within the classical habitable zone. This does not mean Mars becomes habitable. Mars lost its magnetic field 4 billion years ago. Without a magnetic field protecting it, solar wind erosion will continue stripping whatever atmosphere remains. The planet is geologically dead. Its water is locked in permafrost in the polar caps. But the physics of where the habitable zone sits will place Mars in it, a frozen world in the right location. Whether biology could ever reignite there under those conditions, or whether any subsurface life that may have survived in liquid water pockets could surface as conditions warm, is an open question that 1 billion years of solar brightening will eventually pose. Number 5. Earth's axial tilt. It may begin to wobble chaotically. Right now, the Earth's axial tilt is stabilized by the Moon. Earth's axis tilts at approximately 23.5 degrees to its orbital plane. That tilt drives the seasons. It is not perfectly constant. It oscillates between about 22.1 and 24.5 degrees over a cycle of approximately 41,000 years, driven by gravitational interactions with other planets. But it stays within that narrow range. The Moon's gravitational influence on Earth's rotation increases the precession rate of the spin axis in a way that avoids resonance with the orbital precession of the ecliptic. The Moon acts as a stabilizer, keeping the axial tilt from drifting outside its current range. As the Moon moves further away, its stabilizing influence weakens. Models suggest that between 1.5 and 4.5 billion years from now, Earth's axial tilt may begin to undergo chaotic variations. The axial tilt could shift by as much as 90 degrees from its current orientation. An axial tilt of 90 degrees would mean Earth's poles point directly toward and away from the Sun over the course of a year. The equator would be the coldest region of the planet. The poles would experience continuous summer sunlight for 6 months and continuous winter darkness for 6 months. Climate zones as we know them would be inverted. The entire climate system would be reorganized. In 1 billion years, the Moon will be 38,000 kilometers further away. The stabilization will be meaningfully reduced. The onset of chaotic tilt variations will not yet have happened, but the trajectory is already set by the physics. The mechanism is already weakening. By 1 billion years out, Earth's axial tilt will be less well anchored than it is today, and heading toward the regime or chaos becomes possible. Number 4. The Asteroid Belt. Slowly depleted, gradually changed. The asteroid belt between Mars and Jupiter is not static. It has been losing material since the solar system formed. Jupiter's gravity continuously perturbs asteroid orbits. Some are pushed into resonances, orbital periods that are exact integer ratios of Jupiter's period, and those resonances are unstable. Objects in Kirkwood gaps get ejected. Some fall into the inner solar system. Some are thrown outward. The belt's total mass has declined by roughly 99.9% from its original mass over 4.5 billion years and continues to decline. Over 1 billion more years, the depletion continues. The largest asteroids, Ceres, Vesta, Pallas, Hygiene, will persist. The overall number of smaller objects will reduce further. The rate of new debris delivered to the inner solar system will decline proportionally. The increasing solar luminosity also affects the asteroid belt through the Yarkovsky effect, the acceleration produced when an asteroid absorbs sunlight on one side and re-radiates it as heat in a slightly different direction as it rotates. This thermal force is small, but acts continuously, and over millions of years shifts orbits measurably. A 10% brighter sun will increase the Yarkovsky force proportionally. The orbital evolution of every asteroid in the belt will contain the same large objects, but will be even more depleted of smaller material. The rate of new debris delivered to the inner solar system will be lower than it is today. Number 3. The outer solar system. Largely unchanged, but not completely. Jupiter, Saturn, Uranus, Neptune. In 1 billion years, these 4 worlds will look broadly similar to how they look today. They orbit far from the Sun. The 10% increase in solar luminosity will have minimal effects on their physical properties. Gas giants do not have surfaces to bake. Their atmospheres will receive marginally more energy from the Sun. The effects are negligible compared to the enormous internal heat these planets generate. Jupiter radiates 1.67 times more energy than it receives from the Sun. A 10% increase in what it receives changes nothing about its internal dynamics. But the outer solar system will not be completely static over 1 billion years. Orbital mechanics is chaotic on long timescales. The gravitational interactions between the giant planets, particularly between Jupiter and Saturn and the outer ice giants, produce slow secular oscillations in orbital elements. Eccentricities and inclinations drift. The solar system is not perfectly stable. Simulations of long-term solar system dynamics consistently show that Mercury's orbit is the most chaotic. There is a roughly 1% probability that Mercury's orbit becomes sufficiently eccentric over the next 5 billion years that it intersects Venus or Earth. That probability accumulates over a billion years. The Kuiper Belt, the broad disk of icy objects from 30 to 50 astronomical units, will continue to lose material. Objects are continuously skied by Neptune into the inner solar system, where they become short-period comets or ejected to interstellar space. The rate of new comets reaching the inner solar system will gradually decline. The Oort cloud, the spherical shell of comets extending to perhaps 100,000 astronomical units, will be very slowly perturbed by the galactic tide and occasional passing stars. A small fraction of Oort cloud objects will be sent inward, but the Oort cloud is so vast that it will be essentially unchanged on a billion-year timescale. Number 2. The supercontinent that comes and goes. Pangea Ultima. Then breakup. All within the next billion years. Earth's continents are moving right now, at roughly 2 to 5 centimeters per year, about the rate your fingernails grow. On geological timescales, that speed is enough to reshape the entire surface of the planet repeatedly. The continents are currently in a dispersed configuration. North and South America are moving away from Europe and Africa. The Atlantic Ocean is widening, but the Pacific is shrinking. The subduction zones around the Pacific Rim are consuming oceanic crust faster than the mid-ocean ridges are producing it. In approximately 250 to 350 million years, all of the continents will have merged again into a new supercontinent. The current leading model calls it Pangea Ultima. It will form primarily in the tropical region, a single landmass covering roughly a third of Earth's surface, surrounded by one global ocean. Then, within the window of our billion-year frame, the supercontinent will break apart again. The internal heat of the mantle, still operating at that stage, will drive rifting. Pangea Ultima will fracture, fragments will drift apart, new ocean basins will open. The cycle will be repeating one more time before plate tectonics begins to slow toward eventual shutdown. In 1 billion years, the continents will be in a configuration that has no analog in any geological period humans have ever studied. Not recognizable from any current map. Different ocean shapes, different mountain ranges, different coastlines. The planet below the dying surface will have been rebuilt from scratch since today. Number 1. The solar system as a whole. A quieter, warmer, stranger place. Stand in space 1 billion years from now and look at the solar system. The sun is 10% brighter, slightly larger, slightly yellow-white, still in the middle of its main sequence, still 5 billion years from becoming a red giant. Earth is a dim reddish-brown planet, hazy atmosphere, surface temperatures averaging 47 degrees Celsius and rising, no large oceans visible from space. The blue is gone. Whatever life remains is invisible at this scale. The moon is further away. The tidal forces on Earth are weaker. Earth's days are slightly longer. Tidal braking has continued to slow the rotation. The moon looks slightly smaller in the sky than it does today. Mars sits on the inner edge of the new habitable zone, still cold by Earth standards, still thin-aired, but receiving meaningfully more solar energy. Its polar ice caps may be slightly reduced, its surface temperatures slightly less extreme. Jupiter and Saturn remain largely as they are today. The Great Red Spot, if it has survived, still spins. The rings of Saturn have been discussed as eroding over 100 to 300 million years as ring particles rain into Saturn's atmosphere. In 1 billion years, the rings may be gone. Saturn without rings, a plain golden globe without decoration. The asteroid belt is quieter, fewer small objects, fewer new impacts on inner planets. The outer Kuiper belt and Oort cloud persist essentially unchanged, ancient reservoirs of ice in the cold, dark far beyond Neptune. Everything in the inner solar system has been reorganized by a single variable, a star that is 10% brighter than it used to be. The change is modest in percentage terms. The consequences spread across every planet, every moon, every atmosphere, every ocean, and every living thing. One number, 10%. A solar system completely different from the one you live in right now. 10 ways. A sun 10% brighter and the slow death of the inner solar system's most hospitable planet. Earth transformed into a hazy, overheated world, losing its oceans to the sky. A moon 38,000 kilometers further away, ending total solar eclipses forever. Plate tectonics grinding toward shutdown as the interior cools and the geological carbon cycle collapses. The habitable zone migrating outward past Earth towards Mars. Earth's axial tilt becoming less stable as its gravitational anchor drifts away. An asteroid belt more depleted and quieter. Outer planets largely unchanged but slowly evolving in orbital chaos. A new supercontinent forming and then breaking apart again, all within the next billion years, and a solar system that has been quietly reorganized by a single variable, the brightness of its star. The solar system is not static. It never has been. 1 billion years ago, it looked nothing like it looks today. 1 billion years from now, it will look nothing like it does right now. Subscribe to Cosmic Hives. See you in the next one.